All right, welcome back to the course. So we left off when we talked about how decision trees are very good at overfitting, and that's because they will continue to split the training data up with more and more questions until all of the leaves are a pure class, or until it cannot possibly split anymore. So how do we prevent this? Well, right, in general with overfitting or with preventing overfitting, what we're trying to do is prevent the model from learning too much from the training data, right? We're trying to prevent it from learning spurious correlations. So there are some ways to do that with a decision tree, and these are the most common ways. So one is very simple. Actually, the first three are pretty simple, but the first is very simple. You just set a maximum depth. So when I say depth, I mean the number of levels. This would be the first level, the second level, the third, the fourth, etc. Until, who knows, we're at the, let's say we're at the 50th level down here. Um, Actually, if this was 50, there would be many, many more boxes. But the point is you can have each level. So you might say, I'm only going to learn 2 levels and then I'll just stop. So in that case, you would only keep these top 2 levels of the tree and you would do no splits beyond that. So whatever, so basically these boxes here just become leaves, and whatever dominant class was in those leaves would be the categorization. So if this leaf happens to have more passes than fails, you might just then use that as your prediction that any testing data row that ends up in this leaf will then be a pass. So that's one way. You just stop the levels. It's a very blunt but effective way to prevent the tree from becoming too complex. Another is to set a minimum number of data points for a split. So that means that if at any one of these boxes, right, there's only so many data points left that's trying to split on. And if the number is below the minimum, then it won't split, and this will just become a leaf. So let's say our minimum is 50. And let's say this actually has 60, so it will still split. This has 70, so it will still split, but this one only has 30 data points to split, so it won't even perform a split. This will just become a leaf. And then this one has 20, and so it also won't split. So you'd have 2 leaves, but these would still split. So these would stop here, but these would split again one more level. And that's important. We'll see this more, but parts of the tree can stop early. So this half of the tree could come to a stopping point over here, but another part could continue for a while. You could also set a minimum number of data points for a leaf. So this is similar to a minimum number to split, but this time it looks at the results of the split. So let's say this has 60 data points here, and we split it, and our minimum leaf data size is, let's say, 20. So if these 60 splits are split into 30 and 30, then this split will be kept. But if the optimal split here puts 50 to the left and 10 to the right, well, that results in a leaf that has less than the minimum number, which is 20. So that split would then not be performed, and it would stop here. There's also pruning. So pruning is a method of training. So you train the tree fully, or you could still actually use some of these others. So you could still use a minimum number of data points for a split as an example. You could still use, but then you let the tree train fully with whatever settings you have, and then you go back and you start removing splits. So that's why it's called pruning, because now your tree is fully trained, and then you go back and you start removing parts of it to make it less complex. And you usually set the amount of pruning using a cross-validation loop. So it's a lot like how we used a cross-validation loop to set the optimal regularization parameter for logistic regression. So it's similar to that. So you would test different levels of pruning via cross-validation before you found your optimal level. Now, scikit-learn does not support pruning, so we're not going to use it. But it is another popular method of preventing overfitting. All right, in the next lecture, we'll talk about preparing training data for decision trees. All right, welcome back to the course. So now we will talk about preparing training data for decision trees. And just a warning here, I'm going to say one thing and then I'm going to kind of contradict myself a little, um, but it'll make sense when I do. So one thing we haven't talked about yet is data preparation for decision trees. And you remember that when we trained logistic regression, we learned how important it is to prepare your data. You can't, if you have features that are words, so for example, the mom's job, um, you and the values, sorry, the values are teacher, other, service. So they're words. You have to convert those to numbers because they're going to be used in a mathematical equation. Well, for decision trees, you don't have to do that. So if you just think of the data, you could certainly ask a question of the data without the data being all numbers. You could ask, does the mom's job equal teacher? And that's a yes or no question. So in general, decision trees do not require data preparation, or at least they don't require you to convert features with words to numerical features. So now, having said that, here I'm going to contradict myself. The scikit-learn package itself does not support categorical data that are represented as words. So for that reason, because we're using scikit-learn, we still have to convert our data to numerical data. And we want to do it in the exact same way, or almost the exact same way that we did with logistic regression. So we want to use the dummy encoding for all the same reasons we did then. And if you want to review that, you can go back to those lectures. There is one difference. We do not have to drop one of the dummy variables. So we talked about with logistic regression, if a certain category has 5 values, then when we convert it to the dummy variables, we only convert it to 4 columns. So let's take the mom's job, for example. And right now I don't remember all the options, but I think it was teacher, other, service, and health. So that's actually 4. So let's say there's 4 values: teacher, service, other, and health. With the dummy encoding, we'd actually only convert those to 3 columns. So let's say it's teacher, which would be 1 or 0, service 1 or 0, and other 1 or 0. And only one of them can be 1 because the mom can only be one type of job, and the others will be 0. And if they're all 0, then we know it's the last feature, health, that we never give a column to. And we did that because if you add all of them to the training data, if you don't drop one of them, then there can be some issues with the training algorithm. And again, if you want to go back and review those lectures, that's great. Now, because the decision tree uses a different algorithm, we don't have to do that. We can actually keep all of them. And you'll see that when we convert to dummy variables, we keep all of them in this case. One more thing to consider when preparing your data is that you do not have to mean standardize your data. It's not as important in general, and I'll talk about an exception here in a minute, but in general, you don't have to do that. So again, we saw that with regularization, mean standardization can have a big effect on linear and logistic regression, and even some of the training algorithms can perform more efficiently if your data is mean standardized. You don't need to do that with decision trees, again, because they're trained differently. It's not as important. However, I don't want you to think that you can get away with never mean standardizing your data. So a decision tree doesn't require it, whereas a logistic or linear regression, you want to think about it very seriously. You want to think about mean standardizing your training data. But the decision tree doesn't require it. However, there are some data sets where it just makes sense to mean standardize your data because it actually makes a better feature. So I'll give a really simple example. If you are using temperature in a model, it's often, depending on what you're modeling. So let's say you're modeling the deviation in attendance to a zoo. So I'm here in San Diego, and they want to be able to predict what will the attendance be next weekend. And really, they know the average for next weekend, just based on the last 5 years, let's say. But they're more interested in fluctuations that are unexpected. So will there be many more people or many less people? Well, you might look at the weather forecast and you're not really interested in the absolute temperature, but you're interested in the deviation from normal. right? You're interested, is it going to be 10 degrees warmer than it usually is? You might forecast that there's more people, unless you're in a very hot area, and maybe when it gets warm, people stay inside, right? So in that case, you're actually interested in a mean standardized version of temperature, at least a mean normalized. So at least you'd like temperature to be in deviation. So not, is it 75 degrees, but is it plus 10 over normal? So if it's usually 75 degrees and it's forecasted to be 85, then you want your feature to have the value 10 because it's 10 over normal, right? So it's the temperature anomaly. And sometimes you want to standardize that. So you wouldn't even say it's 10 degrees over normal. You might say it's, 2 standard deviations over normal, depending on how you standardize. And that's a whole nother topic, but I work with weather data a lot. So much of the time it's mean standardized for those reasons. Another example is, let's say you have a model and you want to forecast, the purpose of the model is to forecast if a house will sell it or not. And one of the features might be the deviation of the listed price from the mean price of that area. So if the mean price for the houses in an area is 400,000 and this is listed at 440,000, then it's 40,000 more than the mean price, and that might have some effect on how easily it sells. But if the mean price of the house is 5 million, of the houses in the area are $5 million, so now you're in a very, very wealthy neighborhood, then a difference of 40,000 isn't as significant, right? So in that case, you'd want to standardize the differences with respect to the area the home is in. And those just make better features. Those features actually become more informative no matter what algorithm you're using for the problem you're trying to solve. So I guess what I'm saying is, I don't want you to think that just because you're using a tree, you never have to worry about mean standardization. Okay, I think I've said enough about all that. So now we're going to train some trees and look at them, and it'll be fun. So I'll see you in the next lecture. All right, welcome back to the course. So now we are going to train our decision tree. And we first need to read in our data. So we're reading in the training and testing data just like we had before for logistic regression. And we are dummy encoding it just like we did before and splitting it into features and the target. Now there is one difference actually. We are not setting the drop first keyword argument to true. That was a keyword argument of the get dummies function. We talked about in the previous lecture why we don't need to do that. So we did do that with logistic regression. We're not doing it here. Okay, now let's train our tree. And you will see that the code is very simple and the workflow is very similar to training a logistic regression model. We use the decision tree classifier class from scikit-learn, and we make our classifier object, and we set any options we'd like to set over here, or as the keyword argument. So if you remember with logistic regression, we had different arguments like regularization, cross-validation folds, etc. So for our first tree, we're just setting one, and that is the random state argument. And there is a random part of the training that I'll talk about in a moment. And by setting the random state, it just means that every time we run this, that random behavior will actually be the same. So we can run this multiple times, get the same results every time. And also when you run it, you should get the same results that I get. So what is that random part of training? Well, consider when the training algorithm is learning on the training data and trying to find the best split using the Gini impurity. Well, what if multiple splits are tied for best, right? Which is very possible. So multiple splits actually tie for the best Gini impurity score. Which one do you choose? Well, that's the random part. So by setting this, we can ensure that you and I get the same results when we train the tree. So first we create the decision tree classifier, and then we use the fit method to train it, setting our x values to xtrain and the y to the ytrain, which is, of course, is our pass fail column in the training data. So again, it's very similar to training logistic regression. We just use the decision tree classifier instead. And then we see the decision tree that we have created. I mean, we see the options. So you see the default values for all the different options that you can set. But we made a tree. In 2 lines, we've made a tree, right? I mean, we read in the data, that was more lines, but in the actual training, it's just 2 lines. Okay, well, now let's look at the tree we've made, right? That's the good part. So in the next video, we're actually going to look at what the heck this tree looks like.